what I want to do here is basically to introduce you to the concept. And linear programming itself is a simple concept. Very often, it never gets taught in most algorithm courses, right? I think that's not reasonable because you should know how to formulate something as a linear programming problem. But beyond formulating, there isn't a whole lot that you need to know. Okay, so it's something you can get some familiarity with the problem and be exposed to the topic, but not have to really go much beyond that. And that's why we will just spend maybe 20 minutes on this topic and no more. And by the way, there are videos from the last time I taught this course, okay, which when I went a little bit deeper than what I'm planning to do today. Okay, so if you are interested, you should just go back to those videos which are available from the course homepage. Okay, whereas every video that you access from the YouTube page is one which corresponds to the current offering. So you know where the old videos are and where the new ones are. Okay, so linear programming is sort of we have been talking about optimization problems, right? So some optimization problems could be solved using the greedy approach, and there are others that can be solved using dynamic programming. Okay, and here is another class of optimization problems where all of the optimization problem can be stated as a set of linear inequalities. Okay, so there is the problem has you formulate the problem as a set of constraints, right? So a set of linear. The constraints are all linear equalities or inequalities, and then you have some quantity that you want to maximize or minimize, right? So we'll just let's talk about just maximizing, because minimizing is just the dual of the problem. So for instance, consider this example. Okay, so there is a factory that can produce two products, right? So product P1 and product P2. Okay, so obviously people want to maximize their profit, right? So you want to know how much profit you generate for each product. So P1 generates $1 profit per unit, and P2 generates $6 profit, right? So obviously, if you would like to spend your resources towards producing P2, if possible, because that gives you more profit. Okay. But then there is, of course, there is a constraint. You can't just sell everything you produce. There is a market only for so much. So it says that up to 300 units of P2 can be sold, but no more. Okay. And there is also a capacity constraint, right? So the factory cannot produce more than 400 units altogether, right? And now you want to maximize the profit, right? So if you state this as a linear programming problem, then you say, okay, I want to maximize x1 plus 6x2, where x1 is the profit profit per unit for product P1, and x2 represents the profit per unit for product P2, right? And then this constraint, right, so is stated here. X1 is less than or equal to 200, and x1 is the number of units of product P1, and x2 is the number of units of product P2. Okay, and the profit is x1 plus 6 x2. Right, so that is the one that you want to optimize or maximize. And you have this constraint. X1 you can have up to 200. X2 you can have up to 300. And but the total has to be less than or equal to 400, because that's how much you could produce in the factory. And well, if I tell you a problem like this, it's intuitively obvious that you cannot produce negative number of units. But when you pose it purely as a set of linear inequalities, you need to actually capture that as an explicit constraint. Okay. So now what you want is you want to maximize the profit. So, so I'm saying here it is easy to see that the maximum should be at a vertex. And why is it easy to see? Okay, so first what you need to do is you need to say, okay, so what does this quantity look like? x1 plus 6x2. Okay, so x1 plus 6x2, so that defines the profit, right? So P right? And so for different values of the profit, right? Profit equal to 600, this is that line, okay? Because this is x1, this is x2. So if you plot the line x1 plus 6x2 equals 600, then this is the line you get, right? x1 plus 6x2 equals 1200, that is the line you get, right? So the slope of the line is obviously going to be, something like, it's going to be 1 by 6, right? Because it's always, the slope is not going to depend upon the value of p, right? It's only going to depend upon the coefficients of x1 and x2. So the slope remains the same. So corresponding to different profit values, your line goes up or down, okay? Now, you can also see that all these constraints will end up forming some kind of a polygon, right? And what you want here when you maximize is you want to keep pushing this up and up and up, right? And when you start, part of the line is inside the polygon, right? And you want to try to keep pushing it until it just goes outside the polygon, right? And where is it going to go outside the polygon? It's clear that it's going to go outside either here or here or one of those places, right? Because essentially, as you push it up, the length of this line that stays within the polygon is going to reduce as you go towards the vertices, and it is going to become 0 when this thing just touches the vertex. Okay, so that is sort of the crux of linear programming solutions. That is, in order to find the optimal solution, what you need to do is you need to consider, each of the vertices of this polygon formed by these constraints. Okay, and you can evaluate what is your profit function, right, at each of the vertices, and wherever it's maximum, that's where you stop. Okay, and in fact, you don't even have to consider all of the vertices. If you find a vertex such that, let's say you take this vertex, you'll find that the profit here is greater than here and here, okay? And that's enough to guarantee that this is the maximum, okay? In other words, a local maxima is actually a global maxima in this particular context. Okay? I'm not going to tell you why that is the case, just take that as a given, right? I gave you the intuition why the maximum is at a vertex, but I'm not going to try to convince you that that if the profit is maximum, locally maximum, then it's also a globally maximum point. So the well-known technique for doing solving this problem is called the simplex method, okay? And the simplex method simply starts from some place and it keeps trying successive vertices until it finds a local maximum, right? And once it finds a local maximum, then it's going to go for it. So for instance, it's going to compute the value here, then it's going to compare, let's say, then it's going to compute the profit value at its neighbors. Whichever has the lowest value is going to go to that, okay? And then from there it's going to consider its neighbors, and whichever has the lowest is going to go there, right? And ultimately when it reaches the point where the neighbors, all of them have higher cost or return lower profit than that particular vertex, then you say you have reached the solution, and that is the optimal solution to the problem. Okay? So, by the way, the regions that are formed by these sets of inequalities are called convex polygons, in the sense that, so for instance, a concave polygon is, right? So this is a convex polygon, whereas a concave polygon will, could be like this, right? So you can see that that is a concave polygon, right? So there is, so the point is that if you have a convex polygon and you draw a line, well, the line will only cross it, twice, right? Whereas here, if I draw a line, it can cross it, multiple times. Okay, and so if you just specify a bunch of inequalities like this, it'll end up being a convex problem, and you can. This technique will work on the convex problems, and will be able to give you a solution. So again, this is spells out the thing. So you start somewhere and switch to the neighboring vertex to see if the objective function is higher. Then you move to that neighboring vertex, and then you keep repeating this step until you reach a local maximum, at which point you say, I'm done. Okay, so this is an example with 3 products. Okay, so obviously we can still visualize up to 3 variables, because 3 dimensions we understand. But once you go beyond 3 dimensions, obviously we cannot draw pictures and we cannot understand. So I want to just talk about, give you an example of just one more problem. Okay, and this problem I want to talk about because it's somewhat related to, it's closely related to the max flow problem that we will be talking about next. Okay, so here is a network, right? So there are 3 users, A, B, and C, and they all want to communicate, but the rates for communication are different, right? So A, B, for A and B to communicate with each other, they are willing to pay $3 per unit. And for B and C, they are willing to pay $2, and for A and C, they are willing to pay $4 per unit of, let's say per megabit, per megabyte or something like that, right? So that's what they're willing to pay. Okay, and there is a constraint that you cannot have. You cannot tell somebody, I'll give you no bandwidth, right? So there is a minimum of 2 units per connection. So each of them must have at least 2, or else you are not going to. Somebody will be upset if you just tell them, well, you're not paying enough, therefore I'm not going to give you any connectivity, right? So that's the constraint. In order to model the problem, we are going to make note of the fact that in order to go from A to B, there are actually 2 paths, right? So there is a short path and there's a long path. Okay, so you could route the traffic either way, and obviously there is an impact. If A to B traffic goes through this link, then obviously that takes away some of the bandwidth that could be used for going from A to C, right? So one needs to sort of keep that in mind. Okay, and now the constraints of the problem, most of which are implicit, are stated over there, right? So you can see you want to maximize the profit, right? So 3 times, so A to B traffic, right? So will be is labeled as XAB and X prime AB, right? So XAB represents the amount of traffic that's going to go through the short path between A and B, and X prime AB denotes the amount of traffic that's going to go through the long path between A and B. Okay, so now you have this equation which says that A to B traffic pays $3, so the quantity that you want to maximize is 3 times XAB plus 3 times X prime AB, and then $2 to B to C, so therefore you have a multiple of 2 for the XBC and X prime BC, and $4 for A to C connection, so you have 4 times the multiplier for XAC and X prime AC is 4. Okay, and now the rest of it is capturing the bandwidth constraints that are here, right? So for instance, it says that whatever you are trying to send to B could be coming through here and here, right? But ultimately they have to go through this link, right? So they cannot be greater than 10, right? So that's the second equation saying XAB plus X prime AB, right? And in addition, so the traffic that's coming to B is either coming from A or C, right? So that's why we have these two, XAB plus X prime AB plus XBC plus X prime BC. The whole thing is less than or equal to 10, right? Because all of that needs to go through this link, which has a width of bandwidth of 10. So all of the other equations are just these 6 equations, all of them are capturing constraints about each of these 6 edges, right? So there are 1, 2, 3, and then 4, 5, 6, right? So you need to capture the constraints about all of those edges. So those are the 6 equations. And finally, the minimum 2 units per connection, that's these 3 equations. Yeah?
So for the second equation,
yeah,
shouldn't it be greater than or equal to 10? Because it has to go through...
No. What you're saying is that a valid assignment should not exceed the capacity.
Oh,
right?
This is the capacity.
Right. So this 10 is the capacity.
Oh.
Okay? So if that was not clear, that's what I should have made clear right in the beginning. All of these numbers tell you the capacity, right? The bandwidth of each of those lines. Okay? So obviously, valid traffic assignment shouldn't exceed the available bandwidth. And that's what all those 6 equations are captured. Okay? And you do this and you throw it into the system, and the system comes up with a solution. Okay? So this happens to be the solution. Okay? So so what is the profit you make? Let's see whether I have the actual profit written down, or are we going to calculate it here? Okay, so the profit with this assignment is there is 7 units of AB, which is right, 7 times 3 plus 1.5 times no, 3 times, sorry, right? So you have XBC and XBC prime, each is 1.5, so total traffic between B and C is 1.5 plus 1.5, which is 3. And that fetches $2 plus XAC plus XAC prime together is 5. So we have 5 units going between A and C, and that gives you, right, $4. Okay, so now, so that's 21 plus 6, 7, 6 equal to 47 units, right? So, it's what's interesting is that if you think about a greedy approach to solving this problem, right? and for the moment even ignore this constraint, right? This is obviously having an impact on how much profit you can make, right? If this constraint were removed, right, then you'll make more profit, right? Because that's additional constraint, right? So if you remove the constraint, then you should have more valid solutions, right? If you have if the set of valid solutions is larger, that means your objective function can only become higher, right? Because you already have, including this constraint, you have a solution that generates $47, right? So if you relax one, then you still have the solution. This is a valid solution, but may not be optimal, and you may be able to find even better solution. Okay. So now let's try a greedy approach. So we know that C, right? The traffic between A and C generates the maximum profit, right? So we could say, let's try to, maximize this, right? So the limit here is this link, right? So you could just do at most 8 units of traffic you can send from A to C, right? So that'll give you 8 times 4, right? But now C is completely maxed out, right? C cannot talk to anybody more. That's it. It's done, right? So now the only possible communication is between A and B, right? A has already used up 8 of its 12, right? So A has only 4 more left, right? So you have 4, which is fetching 3. So that's 44, right? So even if you are willing to relax this constraint, you still your greedy approach ends up finding a solution that's less than what linear programming is giving you in spite of these additional constraints. Okay. So anyway, again, it just shows you that the greedy approach doesn't necessarily, often fails. So I'm not going to talk about all of this anymore. So we talked about what is a simplex algorithm already. All we are going to do is okay. So let's just talk a little bit about if instead of thinking about the two-dimensional problems where we are able to visualize the polygon and so on, we need to think about what happens when you have n variables, right? So if you have n variables, right, n quantities, that means you have a n-dimensional polyhedra, right? Just like in with two variables, you had a two-dimensional polygon, right? So now, if you have n dimensions, then you're talking about, if you have n variables, then you're talking about n dimensions and objects in this n dimension. Okay. So what's a vertex in this dimension? Where it's a point where all of the n inequalities intersect, right? Or right. So there are n variables. Remember that the number of constraints could be larger than n, right? So if you look at this problem, right? So we had 2 variables but 3 constraints, right? And you can imagine that you could have 10 constraints on 2 variables. That's fine, right? So the number of constraints can be much larger than the number of variables. But the point is that each constraint is, so each constraint, you can think of it like an equation, right? So if you think about n equations, right, on n variables, they have one solution, right? That's why when you bring all of these n inequalities together, they have a unique solution, and that becomes the corner or the vertex, right? So again, if you think in the 2 dimensions, what happens is that you have 2 inequalities, they intersect at one point, and that becomes one of the vertices of your polygon, right? In the n dimensions, again, what happens is that you have these n different constraints, and when you bring them all together, they meet at one point, and that becomes a vertex. Okay, and because any possible right, so you can show that the number of such vertices is m plus n choose n, right? Or let's say, if you don't understand why it's m plus n choose n, just think of it as m choose n. That's easier to understand, right? So you have m inequalities. Any subset of these m inequalities will correspond to one corner, right? So there will be m choose n, which is still exponential in n, right? It's exponential in n and n, right? So that tells you that even though the simplex algorithm seemed like a simple way to do it, you just go from vertex to vertex. In higher dimensions, it becomes an exponential algorithm, right? So in fact, simplex algorithm has a worst case upper bound that is exponential. Okay, so which was so pretty much that's all I want to talk about linear programming. So what it means, how do you formulate something as a linear programming problem, what is the simplex method and how does it work roughly, what is its complexity, and sort of talk about the history of linear programming itself, right? So, in modern times, in 1930s, Kantorovich applies this problem to applies linear programming to problems in economics, and then Koopmans applies it to shipping, right? And at this point, algorithms for doing solving linear programming problems have not been really developed. Then Danzig in 1947 comes up with the simplex method. So it's obviously a very old algorithm, and it's still very much being used today. So in 1975, Nobel Prize was given for this linear programming discovery, except that the person who discovered the algorithm is not the person who gets the Nobel Prize, right? Because obviously it's a Nobel Prize for economics, right? There's no Nobel Prize for computer science or mathematics, right? So you need to be an economist. So economists, so people who apply some algorithm to economic problems will be the ones that get the Nobel Prize. Right? So you might remember in our very first lecture, I introduced this stable marriage problem. We talked about it just for the briefest period of time. That is also an algorithm, but the Nobel Prize for that was given in the field of economics, right? And some of you might have seen this movie called Beautiful Mind, right? So that's about, again, this game theory work, which is primarily, one might say, it's largely computer science type work. But again, the Nobel was given in economics. So if you want to do research in computer science, dress it up as economics, then you might, be able to get a Nobel Prize. Okay, so anyway, right. So Danzig was left out of that Nobel Prize. Later on, because it's an exponential algorithm, simplex is an exponential algorithm. People were looking for polynomial time algorithms. So in 1979, there was this algorithm called ellipsoid algorithm that was discovered. It's a polynomial time algorithm, but it was one of those theoretical algorithms which didn't produce very good performance in practice. And then Karmarkar in 1984 came up with another technique, which ended up being polynomial and also giving more reasonable performance in practice. So I remember I was an undergraduate when this news came out, and it was big news. especially because I was in India at the time, and then there's this Indian guy who discovered some, solved some problems. So it was just big news there. Okay, so that's all I want to say about linear programming. So then we go on to the next optimization problem, which is actually you can think of it as a special case of linear programming, except that this special case is quite important and it can be solved more efficiently than linear programming. Okay. So the basic problem is that you have some kind of a network and you want to maximize what you can send through it. Right? So notice that you are just saying the problem that we'll try to model with the network in the linear programming unit was one that maximizes profit. Right? So here we are not trying to maximize profit. We are just saying we want to maximize the quantity of material that is transferred from point A to point B. Okay? So that's the max flow problem, and it's something that obviously comes up in networks of all kinds, right? Oil networks, electricity networks, communication networks, and so on. Okay? So we'll illustrate max flow using this example. Okay, so here is your source. Right, so when you talk about flow algorithms, there is usually a source and a sink. Okay, the notation that we typically use is S for source and T for sink. Okay, and you want to maximize the amount of material that you can transfer that can flow from S to T, and these edges have directions, and each edge has a capacity. Right, so you can send up to 4 units on this edge, up to 3 units on this edge, and up to 3 units on that edge. Okay? And so you need to figure out what is the maximum that you can send through, and also how to do that. Right? What assignment should be made to each edge so that you maximize the flow from S to T. Right? So that is the problem that you want to solve. Okay, so yeah, again, the edge capacities can be exceeded, right? So the FE denotes the actual flow on that edge E, right? And CE denotes the capacity of the edge E. So except for source and sink nodes, whatever comes in should flow out, right? Because otherwise you have material piling up in one node, right? So there is, you don't have a place to store, anything. So whatever comes into this node C has to flow out through here, right? So it can come in through these two places, and it has to all flow through that, right? So even though that constrains, for instance, so if you look at vertex A, it can, up to 13 units can come in, but only 2 units can go out, right? So that means that some of the capacity of the incoming links into A will not be utilized, okay? So subject to these, this incoming traffic should be equal to outgoing traffic is something that you can model as this constraint, right? So if you all the traffic coming into you from different W's, right, should be equal to the traffic that's going out of you to all its neighbors, right? So that's what that equation says. So yeah, again, it can be posed as a LP problem, but if you just apply a general LP solution, it can be somewhat inefficient. But still, it's actually good to do that, because by applying the LP algorithm, you can actually figure out, okay, what does it do? And based on how the LP algorithm works, you can take that as a starting point and further simplify the algorithm or make some parts of it more efficient, and then that way derive a better algorithm. Okay, that's what happens. Although I'm not going to sort of, look at that. Okay, so instead of trying to explain to you how the simplest algorithm will come up with the solution, we will just go directly to the improved algorithm that you can derive from simplex. Okay. So, but in order to do this, we need to define the notion of a residual graph. Okay. So a residual graph basically captures the remaining capacities. After, let's say, when you are doing this, you're going to do this step by step. In the first step, you might have assigned some flow on some of the edges, right? So now, because you already assigned some flow, the available capacity is reduced, right? Because let's say originally there was an edge which had a capacity of 5. In the first step, let's say you have already used up the capacity of 3. Now what is left is 2, right? So your residual graph basically captures leftover capacity after you have done some initial assignment. Okay, so at the very beginning you haven't made any assignment. Okay, so you the current flow basically says nothing, right? Nothing has been established. So at this point, the residual graph is going to be your original graph because no capacity has been assigned, so all of the original capacities are fully available. So your residual graph is exactly the same as your original graph. Okay? So now what you're going to do is you're going to go through one step of this algorithm, which involves finding one path from S to T and assigning a flow to it. Okay? So you're going to use some path finding algorithm from S to T. Let's say you could use Dijkstra, or you could use simple breadth first search, right? And let's say you find a path. It doesn't matter really at this point how you find the path. Let's say these thick lines spell out the path between S and T that you have identified. Now the maximum flow that can go through this path is given by the minimum of these edges, right? Because you can send 3 here, but ultimately if it has to go through this link, well, that link is going to limit the capacity to 1, right? So what you can push through this whole path is just 1, right? So you have to take the minimum of all of the capacities of the edges on the path that you have sketched from S to T. Okay? So you're going to, so in the first step, what you're going to do is you have picked this path S, A, D, C, E, T, and you're going to push 1 unit of flow through that path. Okay, so now what I just said, right? So this 1 unit is being pushed through that path. That is the current flow, right? Now what is the residual graph? Residual graph basically says that you have used up that capacity. Okay, so this edge, thick edge, used to be 3 because you used up one of the capacity. So what is left is 2, right? So you can push 2 more, right? There is also, you can see that the edge is in the opposite direction. And what it says is that if later on you change your mind, right, you could basically cancel the flow that's going through here, right? Already there is 1 unit of flow going through here, this edge. If you cancel that, that's equivalent to sending 1 unit back, right? So the residual graph has to capture not only what additional oil you can send through, but also what flows could be turned off or reversed, right? So so the point is that this gives you flexibility, because if you, let's say, blindly choose a path and send some traffic through it, it may end up that this is the wrong decision, and then you may have to revert it. So let's see a simpler graph where you can sort of see this happening, right? So let's say here is the graph, right? So taking the simple graph, right? It's pretty obvious that this gives you maximum flow, right? And if you want to achieve maximum flow, there should be 0 here, right? Because you can send only 2 out of S and 2 into T, so obviously you have already maximized how much can be sent. And once you have done that, then 1 is coming in, 1 is going out, so this has to be 0. But if you simply find a path and push something through it, right? So you may end up picking this path, right? So if you got to this state, then you might think that you're stuck, right? Because, well, this is already holding 1, so you cannot send 1 unit here, because if you send 1 unit here, there's already, the 1 unit coming in here, so you cannot take anything more. But when you think of the problem in terms of, okay, although I have sent 1 unit here, I can always reverse it. Then in the residual graph, after sending 1 here, you will have actually a way of going back there, right? There will be an edge with that going in the direction, and therefore you would be allowed to take this path, right? And now if you combine this path with this path, right, you will get the same graph, but these flows going in opposite directions will cancel out, right? So you will get to the solution even though somewhere along you seem to have made a decision that was not advisable, but still you are able to get to the final solution because you are explicitly modeling previous decisions that you have made, and in the algorithm you have a provision for reversing those decisions. Okay, so this is so that's what happened here. So on this path we sent 1 unit. So you will see that for each of these edges there will be a reverse edge showing that 1 unit flow could be reversed in the future. Okay, so that's the residual graph. Okay, so now in the next step, what you're going to do is you're going to find yet another path. Okay, now notice that if you find a path in this residual graph, there is no longer a way to go from D to C, right? Because originally there was just 1 unit capacity here, and you already used up that capacity, so there is no longer an edge in the forward direction, right? The only thing that's left is, well, you could turn off this, and that could go in the reverse direction. So now if you find a path, you won't find the same path, you will find maybe this path, right? And once again, if you look through the edges, you see that the maximum you can push through is 1. So you add that flow. Now together, right, the first step and the second step together result in a graph like this. So originally you sent 1 unit this way. The second time you sent 1 unit that way, right? So the common edges now have 2 units flowing, and the edges that are unique to each path still have 1, 1, 1 on them, right? So the algorithm is simple, right? Each time you find a path from S to T, right? And find the minimum capacity edge on this path, and you say, I'm going to push that much flow through this path, okay? And once you push that much flow, then you modify the graph so that you construct the residual graph instead of the original graph. Now on the residual graph, you're going to repeat the same process, right? So you're going to again find another path, find the least cost edge in that path, push, then adjust the graph so that it reflects the new flow. Keep finding this until you reach a point where there is no longer a path between S and T. Okay? When there is no longer a path, that means you cannot flow. There's nothing more that can be sent from S to T. Okay? So, so again, in this step, you are picking this path.